Welcome to today's Explainer. Today, we're diving deep into exactly how Deepseek systematically mitigates memory bandwidth bottlenecks in LLM decoding. And they're doing this through some really brilliant algorithmic hardware co-design. You see, the physical constraints of modern accelerator hardware have essentially forced a massive shift in how we design large language models. We can't just think about algorithms in a vacuum anymore. We literally have to engineer around the physical metal they run on. Before we jump in, here's our syllabus for today. First, the KV cache bottleneck. Second, algorithmic interventions using MLA. Third, training and routing systems. Fourth, hardware-aware, low-precision serving. And finally, architectural portability. All right, let's start with Section 1, the physics bottleneck. So, to really understand the problem, we need to look at the physics of how generation actually works. You already know the initial prefill phase of a prompt is compute-bound, right? But the sequential generation of tokens, that is strictly memory bandwidth bound. Because the hardware has to constantly retrieve historical key and value states, the KV cache, for all those prior tokens, it's forced to shuttle this data from high bandwidth memory, or HBM, straight into the on-chip SRAM. As context windows get larger, this physical memory footprint just completely dominates your operational cost. It bottlenecks your maximum serving batch sizes for a very simple reason. The GPU physically cannot move data from HBM to SRAM fast enough to keep its compute cores fed. Now think about the structural trade-offs we've seen with existing attention mechanisms. Standard multi-head attention, its cache slice scales linearly, which just absolutely devours memory bandwidth. Grouped query and multi-query were attempts to fix this, sure, but they end up degrading your modeling performance. But then we have multi-head latent attention, or MLA. This is wild because it drops head access memory scaling entirely down to 0. Instead of scaling up with the number of heads, it completely decouples from it, purposely trading that massive memory footprint for higher arithmetic intensity on the compute side. Moving right along to Section 2, algorithmic intervention. Basically, the math. Okay, so how does MLA actually pull this off mechanically? In standard models, you're dumping massive, high-dimensional key and value vectors directly into HBM. MLA completely flips this paradigm. Instead of storing those huge projections, MLA uses a down projection matrix to compress the input hidden state into a tiny, low-rank latent vector. The compression dimension here is significantly smaller than your multi-head dimension. So during generation, only this compressed latent vector gets stored in the KV cache. When you need to calculate attention, it just maps it back up using head-specific up-projection matrices. It's a brilliant move because it shifts that heavy reconstruction burden away from your memory traffic and drops it directly onto the on-chip tensor cores where it belongs. But as we all know, in machine learning, there is always a mathematical catch. Integrating rotary position embeddings, or ROPE, is mathematically incompatible with low-rank up projection. Think about it. If you applied ROPE before caching, you'd be forced to constantly re-multiply latent vectors during decoding, which totally wipes out the memory savings you just achieved. To get around this, MLA introduces decoupled ROPE. It splits the key and query vectors into two parallel streams, a position-insensitive content stream and a position-sensitive coordinate stream. By decoupling them, the position-sensitive component stays completely clear of the low-rank compression pipeline. Boom, you preserve your positional accuracy and keep your memory savings. Now here is where the associative matrix properties come in to save the day. If we had to expand those compressed vectors back into high-dimensional space out in global memory during sequential generation, it would trigger an allocation nightmare. So instead, MLA folds the up projection matrices directly into the query projections. This is the mechanism of absorbed mode inference. It lets the GPU compute the attention natively right there in the low-rank latent space, executing the high-dimensional projection as a single matrix multiplication at the very end of the attention layer. It's just a textbook, elegant example of using algebraic associativity to bypass a hardware bottleneck. Let's move on to Section 3, training and routing optimizations. First up in this section is multi-token prediction, or MTP. We're used to traditional models predicting just the next single token, but MTP modules predict multiple future tokens sequentially at each position. During pre-training, this blasts the model with a much denser learning signal, which drastically improves data efficiency. But the really critical engineering takeaway is what happens at inference time. These MTP modules basically act as a built-in draft model for speculative decoding. Since those secondary token predictions hit an 85 to 90% acceptance rate, you accelerate your generation speeds massively, and you do it without altering the actual output distribution. Next up is routing. If you work with large mixture of experts models, you already know about routing collapse, where a handful of experts end up doing all the heavy lifting. The traditional fix is to slap on some auxiliary balancing losses, but that notoriously degrades your overall modeling performance. So how do we prevent collapse without penalizing the model? Deepseek just ditches the performance-degrading auxiliary losses entirely. They use an auxiliary loss-free load balancing system that dynamically tweaks an expert bias term during parameter updates, all based on expert load. If an expert gets overloaded, its bias drops. Underloaded, it increases. It guarantees load balancing without ever punishing the model for making mathematically optimal routing decisions. All right, let's get down to the metal. Section 4, hardware-aware low-precision serving. Check out how FlashMLA compiles this onto the hardware. It uses a hyper-optimized 656-byte contiguous block for every single cache token. It allocates 512 bytes for the quantized FB8 content, 16 bytes for dynamic subtile scale factors, and, here's the crucial detail, a precise 64-byte allocation for unquantized BF16 rope. By keeping that positional coordinate stream in unquantized 16-bit format, the model rigorously protects positional accuracy while you still get to reap the immense bandwidth savings of those compressed FB8 latent vectors. Now, getting FP8 quantization to work without destroying your fidelity requires a very fine-grained schema. For activations, they use tile-wise scaling on a 1x128 basis, which dynamically wrangles transient numerical outliers token by token. For weights, they use block-wise scaling on a static 128x128 basis, and that static block aligns perfectly with GPU memory layouts for optimal SRAM transfers. This dual approach manages numerical outliers so well that they can apply universal E4M3 quantization across the board, completely dodging the need for messy, slow hybrid formats during the backward passes. There is a hidden trap with low precision math, though. Tensor cores accumulate FP8 math in 14-bit precision. Under heavy accumulation, that can introduce a 2% error rate, which is absolutely enough to destabilize an entire training run. To block this numerical drift, Deepseek uses an increasing accumulation precision framework. The cores execute the initial matrix multiply at blisteringly fast FP8 speeds. But then, at specific intervals, intermediate results are promoted up to FP32 registers, and the final reduction is completed in high precision. This clever maneuver keeps the relative loss error firmly below 0.25% compared to a full BF16 baseline. Which brings us to our final topic, Section 5, ecosystem portability. If you're an ML engineer, your most pressing question right now is probably, how do I actually use these innovations without dropping millions to pre-train a model from scratch? Well, the MHA to MLA framework is the answer. It lets you transition existing pre-trained LLMs directly to MLA. You don't have to rebuild Llama or Mistral. MHA to MLA uses partial rope conversion to identify and strip out the least important positional dimensions. Then it uses low-rank joint singular value decomposition, or joint SVD, to compress the key and value projection matrices together. This cuts the KV footprint of a model like Llama 27B by over 90%, and amazingly, it recovers full downstream performance using less than 1% of its original training data. But what if you're working with grouped query attention models like Llama 3? That's a bit trickier because ROPI is applied to every head, which blocks that absorbed mode math we discussed earlier. To fix this, TransMLA introduces frequency folding and a technique called row rope to aggregate positional information. And for even higher fidelity, you have the CARE framework. CARE improves on standard SVD by utilizing activation covariance. So instead of just compressing weights, it compresses based on activation statistics to stop fidelity drift, dynamically allocating latent dimensions across layers based on sensitivity. Finally, we have to consider hardware realities. MLA's absorbed mode is heavily optimized for the Hopper architecture's specific compute-to-bandwidth ratio. So what happens if your setup lacks Hopper's compute density, like if you're running export-restricted H20 GPUs? That's where Group Query Latent Attention, or GQLA, comes in. GQLA gives you a dual-path capability by grouping the up projection matrices. It dynamically balances your compute and memory footprint based on the exact roofline of your specific host hardware, gracefully resolving tensor parallel bottlenecks along the way. So, what is the big takeaway from all this? Deepseek's structural innovations prove a fundamental point about the future of AI engineering. You don't always need to rely on incredibly expensive hardware upgrades if you perfectly map your algorithms to the hardware's execution properties. By treating the math and the metal as a single, unified, co-designed system, you can unlock immense efficiency gains. I'll leave you with this final exam thought to chew on. If post-training frameworks make it this easy to convert almost any model into MLA, drastically slashing the memory footprint, will the era of relying on massive, brute force GPU clusters soon become mathematically obsolete? Thank you so much for joining me for this explainer.